Hello, and welcome to the Big Bang Hypernova Hypothesis podcast. My name is Stuart McLean, and I am both your host and progenitor of said hypothesis. The Big Bang Hypernova Hypothesis is exactly what its name pertains to be, in that it is a scientific hypothesis relating to the Big Bang theory itself. In one word, hypernova, I am able to convey the entire basis of my hypothesis. The term Big Bang itself is a potential source of confusion, as it can relate to many things. Firstly, the term the Big Bang Theory is itself most popularly associated with a TV comedy show of said name. Of course, this is not Fun with Flags podcast. The Big Bang Theory itself is the observation that our universe, at some point in the distant past, around 13.8 billion years ago, was a much smaller and hotter and denser place. When Albert Einstein discovered his equations of general relativity, the progenitor of the Big Bang Theory, George Lemaitre, noted that a consequence of relativity was that we live in a universe that is constantly expanding. That is, the very fabric of the universe is continually expanding, causing galaxies to move away from one another. Realizing that the universe was expanding, Lemaitre considered the reverse, in that if the clock was rewound, that galaxies would come together as the fabric of space-time contracted. Extrapolating this insight, Lemaitre realized that at some point in the distant past, the universe was a much smaller, hotter, and denser place than we see today. The resultant afterglow of the very early universe, being effectively filled with hot plasma, is seen coming from all heavenly directions, and is called the cosmic microwave background radiation. This, in a nutshell, is what I refer to as the Big Bang Theory itself, namely, the observation that the entire universe was a much smaller, hotter, and denser place than we see today, as evident by the presence of the cosmic microwave background radiation. This microwave radiation has been repeatedly measured, observed, and mapped thanks to both NASA's WMAP and ESA's Planck mission. So, the Big Bang Theory itself is not in contention amongst cosmologists, even if there are old diehards of the steady-state model, but they are a dying breed. Einstein was a believer in the steady-state model himself, until Edwin Hubble managed to convince him otherwise by way of his observations. What is in contention, however, is in trying to find some rational explanation as to exactly how and why our universe came to be a much smaller, hotter, and denser place some 13.8 billion years ago, as evident from the microwave sky. Running a clock back further in time from the moment the photons of the now microwave sky began their journey across the cosmos, we find the entire universe came from a single point of infinite density and curvature, what we call a gravitational or physical singularity, a point where the curvature of space-time is infinite, arising from its infinite density. Or more specifically, it was Stephen Hawking, for his PhD, who took the standard cosmological solution of general relativity, the Friedmann-Lemaitre-Robertson-Walker metric, and by rewinding the clock back on the given mathematical equations, that it was inevitable that the universe was born from a gravitational singularity, a point of infinite density. The simplicity of the Big Bang Hypernova Hypothesis is to say, in order to understand the birth of the Big Bang's gravitational singularity, then let the birth of a known gravitational singularity, specifically a black hole, be the template within nature from which we extrapolate. In order to understand nature, we must study nature itself. This is what physics means, knowledge of nature, and this is central to the Big Bang Hypernova Hypothesis. Of course, the real trouble with my hypothesis now is that after 5 years digging, researching, and effectively trying to nullify it, my hypothesis has grown from a hatchling into being like a 600-ton silverback gorilla that more or less can grand-stomp any competing cosmological models or explanations. I say this in light of completing my essay entitled General Relativity and Rotation, in which I showed how a rotational white hole located in the Eridanus void can perfectly explain the large-scale anisotropies observed on the microwave sky as observed by both WMAP and Planck. Prior to that, I made the prediction that the white hole would be located in the Eridanus void, so in effect, I watched yet another prediction come true, and then I watched the new Kong vs. Godzilla movie. Looking in the mirror the other day, I see my beard having turned to a silver mane, a biological reaction to having the weight of a fully conscious cosmos come crashing down around your head and into your life will kind of do that to a man. Well, it did to me. And that is before we even get into the whole affair of what I simply call the inspirational artwork or symbology. I mean, can any other scientist answer this out of left field question? Is it normal to build an entire cosmological model upon what quite simply is the one and only true biblical Holy Grail? The answer is yes, it is perfectly normal and to be expected, as I look at Dan Brown's series of Robert Langdon books, realizing exactly what they were, namely what is referred to in my trade as a trial run before the actual execution of the event itself. Well, now the deed is done, as I stand back and begin to understand the magnitude of what I've written, effectively enough to show that the Big Bang Hypernova Hypothesis can answer with great simplicity the various questions and problems proposed by other physicists that a cosmological model has to be able to address. To paraphrase the bullet point list on my homepage, the Big Bang Hypernova Hypothesis can, in the context of quantum mechanics, it considers both baryon asymmetry and CPT symmetry, specifically in seeing the formation of a pair of astrophysical jets, each a mirror of the other. In the context of general relativity, in describing how a hypernova gives birth to a rotating black hole that in turn is causally connected to a rotating white hole, this white hole, by a Penrose diagram, is causally connected to a pair of new universes. Looks to explain why we live in a mostly flat universe, as measured from the microwave sky by WMAP, the space of the surrounding superverse, into which our universe is expanding, is itself mostly flat. It looks to explain why we find the universe is closed at the Planck scale, as measured from the microwave sky by the Planck mission. This comes from our universe being an entrapped spaced geodesic or space-time with positive curvature that is causally connected to the white hole that gave birth to it. The large-scale anisotropies identified on the microwave sky by both the WMAP and Planck missions shows how we live in a rotating universe that was born from a rotating white hole. Defining my ideas in terms of a very simple computational model. Show how the cold spot of the microwave sky is actually the heart of the void where the white hole resides. Use my computational model to show how the aligned series of bubble voids identified in the cold spot were formed. Look to explain why we live in a homogeneous universe which arose from the irrotational flow of the vortex nature of the astrophysical jet. Explain the concentric circles identified by Roger Penrose in the WMAP data as the jet unfolds. Sketch out a concentric-shaped reality that emerges in the unfolding of the jet in the context of the second law of thermodynamics, unification of force, and why radioactive decay is invariant to time. To give description to the unidirectional arrow of time underlying the importance of conformal geometry in considering the central axis of the jet underlying the flow of spacetime. To give an origin story in how supermassive black holes came to exist in the very early universe, in reflection of how a hypernova is the alchemical fusion of all elements heavier than iron. Give physical proof of the Big Bang Hypernova's primordial atom, in seeing the shadow of such a universe generating star-like object in the spherical Boites void. Using this description of the Boites void, I define dark energy within my hypernova model. From understanding recursion of entrapped rotating spacetimes via general relativity, I explain dark matter in the context of my model and why it has no particle representation. Explain the formation and observation of Fermi bubbles and how this accounts for the black hole information paradox. Nullify the assumption of a point singularity as described in the Lambda CDM model in considering rotation and the consequences of a ringularity. Present a number of cases which undermine the homogeneous and isotropic principle, particularly in the context of the CMB cold spot, Boites void, and the CMB's large-scale anisotropies. See how galaxies flow around the local void, undermining the accepted explanation for how voids form. And that's only really us at the very start of this exploration. Now, if you feel like I just cast a confundus charm upon you, accept my apologies. Everyone I try to explain this to seems to end up with the same blank look expression. Cosmology, after all, is an extremely specialist subject, of which I have been a lifelong passionate geek. My purpose is not to confuse, but rather to communicate to those who, like me, are in the know. Despite the paradoxical name, the Big Bang Hypernova Hypothesis is rapidly becoming the serious heavyweight contender, and that is before we even discuss Buddhism and its associated cosmological models. Seriously. Oh man, for all you physicists who are true seekers of truth and desire a hypothesis that actually makes sense in considering the deep mysteries of life, well, you're certainly not going to be disappointed. I'm still trying to pick my jaw up off the floor after being blown away yet again by this week's revelation. This revelation comes from a composite image of the Milky Way's galactic core in both X-ray and radio. As the man who coined the term jetaverse in the context of CPT symmetry via helical spirals, I am just counting the ghostly number of jetaverses seen in this image. The very structure of each jetaverse being mirrored in the DNA chromosome, to my eyes at least. Then this week past, there is also the discovery of a giant galactic arc measuring 3.3 billion light years in length. I do love arcs and curvature that defy the homogeneous isotropic principle like the large-scale anisotropies that mainstream cosmologists have been trying to hide for the last few decades. Then there is the discovery of the largest spinning structure in the universe, which I found out about last night. They say theoretical physicists have to wait decades or even a century before their ideas can actually be tested. Life for me these last years has been non-stop revelation and confirmation as I have an idea, and lo and behold, the solution or evidence presents itself as it flows in across my RSS newsfeed, this week being a classical case in point. To be honest, I have watched as repeatedly again and again I have had headshot after headshot in developing my entire hypothesis, a headshot being a discovery worthy of a Nobel Prize in itself. Each one in and of itself is worth a lifetime study and devotion, but to have so many in rapid succession, well, it would be nice to say that I am just that good. No. I'm good, but I'm entangled with a higher power which really wants to make a very specific point. Part of that point is to allow me as a singular man to act with, I guess, divine powers, cause me to run scared of myself. The mantra, "You're human," a prayer of humility as I remind myself of what I truly am in this life. The truth of the matter is that I have the personal backing of that spirit which man in ancient days called Apollo. I simply follow a predestined path that was long planned out thousands of years ago. The problem I really have is that my internal story narrative, which is the locus of my identity, leads to this one and only conclusion. Things look less funny when you employ the unencoded symbology born upon the bone box of the man who prosecuted and sent one Jesus of Nazareth, circa 33 AD, to be crucified in order to develop my hypothesis. I don't think I'll ever get over the fact that the box of Caiaphas has the number of the beast all over it. Certainly the number of the beast has had the effect of turning me into a beast, that I cannot deny. Being ostracized, after all, for me is a way of life, and my comfort zone having been marked by this number by evangelicals in the satanic panic of the 1980s. But tales of wizards and boarding schools in the Highlands of Scotland is a tale for another time. Well, at least on the other hand, I might finally get to talk to a therapist. Maybe I could describe dinner this evening to my therapist. A quiet, happy family meal, the height of luxury for me. What caught my eye during dinner was the engraved woodwork on the back of the dining chair I inherited from my grandparents. I hadn't noticed it before, but suddenly I was looking at the engraving upon the back of the chair. What I saw in the engraving was the cross-sectional pattern of a feeding black hole with twin jet formations. Like the duck-rabbit optical illusion, I could see two flip sides to the artwork. On the one flip side, the horizontal part is the input accretion disk and the vertical, two closed jetaverses. On the other side of the vertical is the closed electromagnetic field lines that capture the input accretion disk, and the vertical were the actual astrophysical jet formations. You see, it is in everything, because fractal geometry is the cosmological principle, and self-similarity repeats itself irrespective of scale. This is not some academic point of highfalutin philosophy. This truth of nature is so fundamental, I see it in a piece of furniture that has always been present in my life for the very first time this evening. It is something that just blows my socks off, and yet again puts my jaw on the floor. Such beauty in the simplest and modest of things is truly artistic genius in my eyes. And for us, this is a good place to begin our journey, as we begin by gaining an understanding of the importance that is the cosmological principle. We cannot recreate the Big Bang in a lab. Simple as, we cannot recreate the Big Bang in a laboratory no matter what we do. And I don't care what the people at the LHC or Fermilab have to say. 1. Because the very metric of space-time at the time of the Big Bang was much smaller than it was today. A meter, or even a light year in length, as it is today, would have been smaller than the size of a quark in the moments preceding the Big Bang event. Secondly, the quantum mechanical versions of the Big Bang, such as quantum gravity or inflation theory, are only valid if quantum mechanics is the underlying mechanism of the Big Bang. By using the theory and results of general relativity, I have laid out reasoned explanation as to exactly what is responsible for the cold spot and the large-scale anisotropies. I don't need quantum mechanics to explain the microwave sky. The Big Bang theory is a prediction of general relativity, and via general relativity, I have been able to explain the microwave sky. This is opposed to the particle physicist's sales pitch to build even larger colliders where general relativity's only relevance in the Big Bang is the determination of scale. So, the Big Bang cannot be recreated in a lab. Thus, I am unable to create an experiment that I can use to test my ideas. There was only one Big Bang event with respect to the birth of our universe, and it cannot be reproduced. The point being that I am forced into making assumptions about the birth of our universe, which acts as the very foundations upon which I build my ideas. The importance of the cosmological principle is that it is the very key cornerstone, foundational block upon which everything else is built. If that cornerstone were later to be falsified, then it would be very catastrophic to everything that was built upon it. The accepted cosmological principle says that the spatial distribution of matter in the universe is both homogeneous and isotropic when viewed on a large enough scale. So what does this mean, and what does it imply? Firstly, it is a statement about how matter is distributed or spread throughout the early universe. It says that matter is evenly distributed throughout the early universe. In other words, for any location in the early universe, the density of matter at that point is exactly the same as every other point in the early universe. This is what homogeneous, meaning the same everywhere, explicitly implies. The second condition applied to the spatial distribution of matter is that it is isotropic. In a nutshell, isotropy is uniformity in all orientations. A good example in thinking about the isotropic nature of the cosmological principle comes from considering the orientation and spinward direction of spiral galaxies. A spiral galaxy has a disc-shaped structure with arms. Stars in the spiral galaxy orbit or rotate around a central core. Thus, the spiral galaxy can be said to have an axis of rotation. That is, an equivalent north-south line can be drawn through the center of the galaxy, intersecting with the supermassive black hole at its core, around which the stars in the galaxy orbit. This axis of rotation of a spiral galaxy is explicitly seen when the supermassive black hole at the galactic core is feeding. The two resultant astrophysical jets each travel in polar opposite directions away from one another. These tight beam jets travel along the axis of rotation and thus allow astronomers to measure the orientation of a galaxy. Now, in saying that the spatial distribution of matter is isotropic, what we are saying is that the orientation of any piece of matter is completely random with respect to all other matter. In the case of spiral galaxies, it means that a given spiral galaxy's axis of rotation or orientation should be completely random. So if I were to sample a piece of the night sky and record the orientation of all spiral galaxies in that region, then I would expect the resultant distribution showing orientation to be evenly, hence randomly, distributed. The galaxies should not be generally pointing in the same direction if the spatial distribution of matter is isotropic. Another example looking at spiral galaxies comes in the spinward direction of their arms, as it allows for a binary measurement. The binary measurement is that we could observe the arms of a spiral galaxy as having either a clockwise spinward direction or a counterclockwise spinward direction. That is, follow the curvature of an arm in a spiral galaxy, traveling from the center to its edge, and look at the curve. The curve is either orientated in a clockwise direction or a counterclockwise direction. Now we measure a large sample of spiral galaxies and measure their spinward direction with respect to how we observe them here on Earth. If the isotropic principle holds true, then there should be no statistical significant asymmetry between the number of galaxies with a clockwise spinward direction versus the number of galaxies with a counterclockwise spinward direction. In other words, there should be no asymmetry between the number of galaxies with either clockwise and counterclockwise spinward directions. Thus, isotropic means that matter has no preferred direction in the early universe. Put this together, we see the standing cosmological principle is the assumption that the distribution of matter throughout the universe is both evenly spread and its orientation and direction of travel is completely random, i.e., the spatial distribution of matter is both homogeneous and isotropic. This is the one single assumption that the mainstream cosmologists have made in building theories about the Big Bang event itself. Now, the reasons for making this assumption are many, with philosophical roots going back to both Copernicus and Newton. Copernicus, who showed the Earth is not the center of the universe, as he first showed how we orbit the Sun along with all the other planets. Patterns repeat themselves. Being as I am the first man to define the superverse, as well as coin the term jetaverse, I can hear the ghostly whisper of Copernicus saying,
They say welcome, brother.
The last piece in understanding this cosmological principle comes in the phrase, when viewed on a large enough scale, i.e., the cosmological principle states that the spatial distribution of matter in the universe is both homogeneous and isotropic when viewed on a large enough scale. The key principle being communicated here is that we have to acknowledge that the very fabric of space-time that underlies our universe has been expanding from the moment of the Big Bang. Because of this expansion, what would have been initially a small metric volume in the early universe will have expanded and grown over time such that its overall spatial volume is now sufficiently large enough. So, this part of the cosmological principle recognizes that what was initially a homogeneous and isotropic distribution of matter has over time coalesced into clusters of galaxies. Thus, in considering this principle in looking out at the universe today, we ensure the spatial volume being sampled is of a sufficiently large enough size when applied to the field of cosmology. The actual figure for a sufficiently large enough size is between 250 to 330 million light years. Putting this all together, I begin by defining a sphere whose diameter is around 300 million light years across. Selecting a point inside our universe at random, we place the center of our imaginary sphere at this randomly selected point. Next, I count the number of galaxies inside the sphere and measure their orientations. I then repeat this procedure by again selecting another random point, placing the center of the sphere at that point, and counting the number of galaxies as well as their orientation. I then continue to repeat this process again and again for the entire observable universe. If the homogeneous part holds true, then the distribution of the number of galaxies counted should produce a normal distribution. If the isotropic part holds true, then a plot of all the orientations should produce an evenly distribution, showing no favor to any alignment. If it is not an even distribution for a given region, then we say that the region has anisotropies. The word anisotropy is going to keep being repeated throughout all my work, primarily because that is what is actually being found. So when we talk about anisotropies, we are talking about the orientation of matter. Specifically, I think in terms of orientation of the axis of a galaxy rotation. This in turn can be directly observed and measured in active galaxies by the orientation of their astrophysical jets. Now, the primary reason that the standing cosmological principle that at large enough scales the spatial distribution of matter is both homogeneous and isotropic has become the accepted view is that when we look out into the night sky, we have consistently seen the same picture over and over again, namely a picture of galaxies containing billions of stars made up of the same atoms following the exact same laws of physics as we are subjected to here on Earth. When measured, a fairly homogeneous and isotropic distribution of galaxies was found. Well, at first. However, as more and more observations have been done and automated processes have allowed for greater and greater data collection, this does not quite appear to be the case. This particularly dates back to the Boomerang experiment in 2000, when the anisotropies on the microwave sky were first detected. When the cosmic microwave background radiation was first discovered, and then subsequently mapped, these maps showed an even temperature distribution indicative of a universe that is mostly homogeneous and isotropic. It has only been in the last couple of decades that more accurate maps are rising from more precise experimentation such as WMAP and Planck. Has there been any actual variation found? It has only been in the last couple of decades, with the advancements in technology, experimentation, and observation, that we have managed to step into the golden age of precision cosmology. The problem now for the homogeneous and isotropic cosmological principle is that the evidence that this assumption is in fact wrong is mounting up on a nearly daily basis. I refer to the two examples I gave prior from this week alone as being a typical case in point. Particular examples that I've covered in previous work include the Boy-2 supervoid. The Boy-2 supervoid is a spherical void of nothingness measuring over 330 million light-years across. Given that a definition of sufficiently large is about 250 million light-years, then by this cosmological principle, there should be around 2,000 galaxies occupying the spherical volume of the Boy-2 supervoid. The Lambda CDM model's explanation, the standard model of cosmology, states that voids like soap bubbles coalesce over time. So from an initial homogeneous mixture over time, galaxies are drawn to one another into clusters and superclusters. Likewise, regions filled with dark energy also coalesce together into forming larger and larger voids. Now, there was a debate that given the size of the Boy-2 supervoid, the amount of time required for such a large void to form was far greater than the age of the universe, 13.8 billion years. But the consensus seems to be that there is no crisis in the Lambda CDM model. Now, if supervoids like Boy-2s take time to form, then what about the Eridanus supervoid, aka the cold spot on the microwave sky? We observe the cold spot both in WMAP and Planck. The conclusion is that this is a supervoid measuring around 1 billion light-years across. Given the Lambda CDM model's explanation for the Boy-2 supervoid, then how did this form only 200,000 years after the Big Bang event itself? I guess it's not statistically significant, and like the large-scale anisotropies can be conveniently swept under the rug. Such a danger does it pose to the existing literature and the foundations upon which the vast majority of cosmology is based. Then we have discovered structures like the Sloan Great Wall measuring 1 billion light-years in length, or the Kuma Wall galactic filament measuring 750 million light-years in length, but that great galactic arc measuring over 3 billion light-years in length is yet another nail in the coffin of this homogeneous and isotropic principle. But the greatest elephant in the room for the homogeneous and isotropic principle comes with the large-scale anisotropies identified on the microwave sky. These large-scale anisotropies have been observed in both WMAP and Planck data, and hence the same results have been reproduced. Coupled to this, the work of Lyar Shamir from late last year. He showed that these large-scale anisotropies are related to the asymmetry of galactic spinward direction and thus most likely linked with the large-scale rotation of the universe as a whole. Of course, a rotating universe to the vast majority of cosmologists makes no sense. Rotating with respect to what? Particularly when your vision of everything is confined to this universe alone, and all that exists and ever will be was contained inside the Big Bang itself. Well, until I came along and invented, or rather discovered, the concept of a larger superverse, of which we are but a subset. The tale of that discovery being recorded in the making of my CPT symmetry film. Notice I do not mention the name superverse before that date, particularly in my original film. So from my point of view, a rotating universe makes sense, because I can say with respect to a stationary observer within the superverse. My real contention with the homogeneous and isotropic principle is that straight up the microwave sky nullifies this cosmological principle. The maps of the microwave sky have shown that these large-scale anisotropies, and for the last 2 decades, this evidence has been effectively swept under the carpet. And for that, I am truly grateful. Okay, I may not be able to get funding or a position inside the university because of my position. That's alright. Because 1,000 years from now, it'll be my name people will speak and remember. The reason I was so successful, where all else have failed, comes down to what I choose as being my cosmological principle. Namely, I say fractal geometry is a cosmological principle. This is my basis and philosophical foundational cornerstone. Coupled with this, I have the very foundation stone of all Western civilization backing me that shows the full might and splendor of this one single principle in full action. Go look at all my work and you'll see. Fractal geometry is a true cosmological principle. So what am I meaning by this? Well, first I need to define what I mean by a fractal. To quote the Wikipedia page, in mathematics, a fractal is a subset of Euclidean space with a fractal dimension that strictly exceeds its topological dimension. Fractals appear the same at different scales as illustrated in successive magnifications of the Mandelbrot set. Fractals exhibit similar patterns at increasingly smaller scales, a property called self-similarity, also known as expanding symmetry or unfolding symmetry. The key sentence I wish to concentrate upon is, fractals exhibit similar patterns at increasingly smaller scales, a property called self-similarity. A self-similar object is exactly or approximately similar to a part of itself. In other words, the whole has the same shape as one or more of the parts. Many objects in the world, such as coastline or fern leaves, are statistically self-similar. Parts of them show the same statistical properties at many scales. Scale invariance is an exact form of self-similarity where at any magnification there is a smaller piece of the object that is similar to the whole. For instance, a side of the coast snowflake is both symmetrical and scale invariant. It can be continually magnified 3 times without changing shape. Thus, the foundation is laid, such that I can formulate the underlying structure that forms my hypothesis about the Big Bang theory and the birth of the universe. Knowing that an unknown gravitational singularity, as evident by Stephen Hawking's PhD, gave birth to our universe, then by studying the birth of a known gravitational singularity, a black hole, we can infer its behavior to a larger scale by the law of scale invariance in order to describe the birth of our universe. And that's it. Period. So to repeat that, Knowing that an unknown gravitational singularity, as evident by Stephen Hawking's PhD, gave birth to our universe, then by studying the birth of a known gravitational singularity, a black hole, we can infer its behavior to a larger scale, by the law of scale invariance, in order to describe the birth of our universe, meaning, by studying the dynamic pattern of how a black hole, which by general relativity contains a gravitational singularity, is born inside our own universe, then we can imagine this at a much larger scale, namely at a scale that is sufficient to account for the mass of our entire universe. And what exactly gives birth to a black hole? In one word, a hypernova. But the subject of what exactly a hypernova is, we will explore in the next episode of the Big Bang Hypernova Hypothesis podcast. Until next time.